All right, welcome to the lecture for July 2nd, where we are going to finish talking about second order homogeneous linear equations with constant coefficients. Okay, so start on the warm-up here. And hopefully paused, gotten the answers. Let's go over the solutions real quick. So for the first one, if we write down the characteristic equation, r squared plus 3r minus 10, want to set that equal to 0, we should get that r is equal to -5 or +2, which tells us that our general solution is y equals c1 e to the -5t plus c2 e to the 2t. For this second one down here, r squared minus 2r minus 4 equals 0. And let's go ahead and actually complete the square on this one. So if we write r squared minus 2r, it can be useful to just put the 4 on the other side. And now if we have that, so if we divide -2 by 2, we get -1. So we want to add -1 squared to both sides. And so we get r minus 1 squared equals 5, or r equals 1 plus or minus the square root of 5. This let us know that our fundamental set of solutions is e to the 1 plus square root of 5t and e to the 1 minus square root of 5t. So our general solution is going to look like this. Okay. So to sort of summarize the tail end of last class, given some equation of this form, so second order linear homogeneous, if the characteristic equation has roots, so the characteristic equation, which is r squared or ar squared has real roots, I should say. R1 and R2, then remember we introduced or sort of talked more about this. So the fundamental set of solutions is e to the r1t and e to the r2t. And the general solution to this original equation up here is y equals c1 e to the r1t plus c2 e to the r2t. All right. So let's just do one more example, practice, a little bit more practice never hurt. So let's find the general solution. To y double prime minus 6y prime plus 9y equals 0. Okay, so, we go ahead, we'll write down our characteristic equation. Oh, we can see that this factors real nicely as r minus 3 times r minus 3. And so we get that r is equal to 3, but sort of twice. Well, we only sort of got one r value. So, okay, e to the 3t is a solution. But we can't just include e to the 3t like twice. So the solution is not y equals c1 e to the 3t plus c2 e to the 3t. Like, this is not true. One way to see that is, well, really, we're only really describing one solution there, but just to double check, you can verify this for yourselves. If I compute the Wronskian here, I get 0. Okay, well, we're kind of stuck. We need two solutions to this. So what we're going to do is something we sort of talked about briefly at the beginning of this section of the course, which is we're going to do a change of variable. And what we're going to do, so I'll use u, is I know that e to the 3t is a solution. So I'm going to do a change of variables, and I'm going to divide by e to the 3t. And recall, why? Well, because this means that in terms of u, like u equals 1 should be a solution. So we should end up with something where we've eliminated sort of this bottom term. And then there we can, do a pretty simple change of variables to solve it from there. Okay. So we have that, and that means that y is equal to e to the 3t times u. We're going to need to compute the derivatives. So this is going to be e to the 3t times u prime plus 3 e to the 3t times u. And here we have e to the 3t u double prime plus 6 e to the 3t times u prime plus 9 e to the 3t times u. So now let's plug all of these into here. So y double prime minus 6y plus, or y prime plus 9y equals 0. So I'm going to pull out an e to the 3t for this y prime just to make it a little bit simpler, and the same for up here. Again, pull out the e to the 3t, and then we're left with u prime plus 3u. And down at the bottom, we got 9e to the 3tu. Okay, let's now pull out an e to the 3t from everything. So then we have a u double prime plus 6u prime plus 9 minus, bring the 6 inside, 6u prime plus 18u, and then plus 9u. We want this equal to 0. Remember, e to nothing is never 0, so we can just sort of forget about that part and just focus on this. Okay. So let's combine the u double prime terms. There's just one. We're left with u double prime. Okay, u single prime, we have plus 6 and then a minus 6 u prime. And for the u terms, we have a 9 minus 18 plus 9u. And after doing some calculations, both these vanish. Okay, so we just got u double prime equals 0. So, okay, u double prime equals 0. We can solve this pretty easily. We just have to integrate twice, right? U prime is some constant, call it C1 because I'm expecting another. And then u should be, well, the antiderivative of a constant is just, we haven't picked a variable, but I guess t. So t plus C2. And now we're almost done. Remember that u is y over e to the 3t. So y over e to the 3t equals just tells us that y equals e to the 3t, or times c1t plus c2, or c1 times t e to the 3t plus c2 times e to the 3t. All right. So we got a double root, and it turns out that our other solution that forms a fundamental set was t e to the 3t. Let's just make a note of that. Let's do one more example of this. So we're going to find the general solution to y double prime plus 2y prime plus y equals 0. So we get r squared plus 2r plus 1 equals 0. And again, we can see, this is r plus 1 squared. So r is -1, and we can't, because we only have 1, again, we don't know necessarily what the fundamental set of solutions is. But let's try it once more with this. So y equals e to the -t is a solution. So let's again do a change of variables. U equals 1 over e to the -t times y. Again, so that we're going to get a constant solution, we can just sort of reduce it to a first order problem. So we're going to have y equals e to the -t times u. Y prime equals e to the -t times u prime minus e to the negative t times u. And y double prime. And just because that was useful, I'm going to pull out the e to the negative t so I can get rid of it right away. All right, so we know what our y primes are. Let's plug it in. E to the negative t times u double prime minus 2u prime plus u plus 2 times e to the negative t u prime minus u, and then plus e to the negative t times u equals 0. Again, we'll pull that out. U double prime minus 2u prime plus u plus 2u prime minus 2u plus u. We can get rid of that again because that's never going to be 0. We should see, oh wow, okay, so that cancels, and we have plus 1, 2 u's, and then minus 2 u's, so those also cancel. And we're left with the same thing, u double prime equals 0. So we can repeat, u prime equals c1, u equals c1t plus c2. And if we recall our sub, 1 over e to the negative t times y equals c1t plus c2. So y equals c1t e to the negative t plus c2 e to the negative t. All right. So I think we've probably seen enough. We sort of get a sense now of what's going to happen every time. Right, we got a, for the first example, right, we had y double prime minus 6y prime plus 9y. We had a repeated root for a characteristic equation. That is, we got r minus 3 squared equals 0. And our fundamental set of solutions was e to the 3t and t e to the 3t. For the second one, we had y double prime minus 2y plus y equals 0. We got r plus 1 squared equals 0, so our root was r equals negative 1. And we had the fundamental set of solutions, e to the negative t and t e to the negative t. So from here we can probably guess that this is going to happen just every time. But let's just confirm that for ourselves. So let's see, if we have a root like this, so if we have r minus, and let's say our root is a, let's work backwards. We're going to get r squared minus 2ar plus a squared as our characteristic polynomial. And so if we look at the differential equation, y double prime minus 2ay prime plus y equals 0, well, oh wait, plus a squared y equals 0. Well, we know this is going to have a double root with r equals a. So now the question we should sort of ask, so y equals e to the at is a solution. What about y equals t, e to the at? Well, let's check it. Y prime would be e to the at plus a times t, e to the at. And y double prime is going to be, let me pull that out because it's probably going to help us. 1 plus at. Y double prime is going to be, well, the derivative of this thing is a e to the at, and then here we have taking the the derivative of this guy, the t, a e to the at plus at times a e to the at. Or pulling out the e to the at and simplify, we get a 2a plus a squared t. All right, so let's plug all of these in, just sort of checking to make sure that these are solutions. And let's see, yep, this thing is going to cancel with, well, that 1 inside, and we have then wait, I think I made a mistake here. Oh, this should be an a squared t. Of course, of course, of course. Okay. All right, so we have that, and then we're left with a squared t minus 2a squared t plus a squared t. And yeah, that equals to 0. And you know, we should also, in theory, at least check that the Wronskian of t and e to the at is non-zero. But I'm not going to really bother with this. So if you haven't sort of noticed by now, anytime you get that the Wronskian of two functions are 0, only when there's some number, you know, k, so that f of t equals k times g of t, or k f of t equals g of t. Now, sometimes, like we saw on the worksheet, if we take the Wronskian of ln of t and ln of t squared, it's not immediately clear that this is the case, but if we bring the 2 down in the front, that works. Okay. So what did we just learn? Well, given y double prime if the characteristic equation has a double root, at r equals r1, then the general solution is y equals c1 times t e to the r1t plus c2 e to the r1t. All right, so I'm going to do one more example of this just because, I like to give sort of more in-depth explanations, but here I'm just going to work through a problem and show the level of work you should do. So let's find the general solution . For y double prime minus 4y prime plus y equals 0. And now let's just show the level of work. Okay, so 4r squared minus 4r plus 1 equals 0. We can factor that. 2r minus 1 squared. And so 2r minus 1 equals 0, r equals 1/2. We get a repeated root. It's not a bad idea to sort of indicate that. So our fundamental set of solutions is e to the t over 2 and t e to the t over 2. Don't necessarily need to show that step every time, but it is going to be useful in a bit, so that's why I'm pointing it out. And so y is c1 e to the t over 2 plus c2 times t e to the t over 2. Obviously, the order of which one is y1 and which one is y2 doesn't matter. They just both need to be there. All right. So we now have looked at what happens when we have two roots, what happens when we have a single root, and there's sort of one case left. So let's look at an example of that. So we want to find the general solution to y double prime plus y equals 0. Okay, well, we can look at our characteristic equation. See that r squared equals -1, which already sort of alarm bells should be going off. Okay, so r is plus or minus the square root of -1. Normally we're not allowed to take the square root of -1, right? But at some point we've learned square root of -1 is a complex number, which, while not the best name, is much better than imaginary. And so, okay, r is plus or minus I. So, naively, this says that y is c1 e to the it plus c2 e to the negative it. Of course, that is not what we're going to do. It's not quite going to be that simple, even though, in some sense, that answer is not technically wrong. But of course, if we're sort of given a real problem, it's always good to try to solve it in terms of real solutions. So let's just look at this a different way. So y prime equals negative y is another way of thinking about it. So go ahead and maybe try to think, can you think of a function whose second derivative is equal to negative what we started with? Okay, well, yeah, how about we get y is cosine of t, right? Then if we take the derivative of that, we get negative sine of t, and y double prime is going to be just negative cosine of t. Similarly, we could do the same thing just starting with sine, right? Y prime is cosine of t, and y double prime is negative sine of t. So both terms, taking the second derivative, we got negative what we started with. But we found two solutions. You can confirm that the Wronskian of cosine of t and sine of t is equal to just 1, or maybe negative 1. I think it's just 1. That was a problem on the worksheet we did on Tuesday. And so we check that. We can say that cosine of t and sine of t is the fundamental set of solutions. And so our general solution is a yc1 cosine of t plus c2 sine of t. Okay, so the question maybe you're wondering is, like, what the hell just happened? So we got a, did everything normal. We got complex, in fact, I guess purely imaginary roots, plus or minus the square root of -1. And then it turned out that the answers was sine and cosine. Well, the answer to that, what just happened, is sort of twofold. So first, there's something known as Euler's formula. And what this says is that e to the it, first of all, Euler's formula in some sense is kind of maybe a definition, but it's a definition that behaves all the like properties we need it to. It's the right definition, I guess. Because of course we have to even say what it means to get this. And it says that e to the it is cosine of t plus I sine of t. I'll also point out, because we'll need it later, e to the negative I t is e to the I of a negative t. And so we can rewrite that as cosine of negative t plus I sine of negative t, which cosine of a negative is just unchanged, and sine of a negative is the negative of the sine. So this looks really, really bizarre when you first say it. And I'm not going to give it a complete description of this, but I will provide a link to a video to a YouTube guy named 3 Blue 1 Brown, who gives a pretty quick, it's 3 minutes long, and it gives a pretty pretty good explanation of why this is true. So just in short, though, so complex numbers are really closely related to rotations, and this is why it's sort of weird to call them imaginary. Like rotations are very concrete. It's something that we need to do a lot of time in physics and computer graphics and stuff. But sort of the main idea is so multiplying. So if we think back to Calc 3, right? If we have a vector, like say AB, a plane vector, we can get a complex number, A plus IB. And it turns out complex numbers provide a solution to a pretty natural question. Or really a really natural class of questions. So what vector do you get if you multiply, or I'm sorry, if you rotate, say the vector 1, 2 by 10 degrees counterclockwise? And then let's also think about it for 90 degrees. So, we can look at this. We have our vector go 1, and then we go up 2. And we want to get this new green vector where we've just rotated it around the origin counterclockwise. It turns out that the answer to this is as follows. So convert 1, 2 to a complex number, and multiply by the complex number corresponding to just like a 10-degree rotation from 1. So 1 plus 2i cosine of 10 plus I So 1 times this gives us I still unchanged, right? Our rule here is just, keep them separate, but anytime we multiply two i's together, make that a -1. So here, let's see, we would get -2 for the real part. We would have cosine of 10 degrees minus 2 times sine of 10. And for the complex part, well, we're going to have sine of 10 and then plus 2 cosine of 10. And of course, there's nothing special about what I'm doing here. If you really want to know sort of how I would rotate a point around the origin in the plane, complex numbers are a really great way of going about that. Really convenient, and it's very hands-on, concrete. You might not be able to answer a question like, oh, what? You're never going to have a question where the answer is square root of -1 apples. It's not like a number in that sense. But like you're probably also not going to have a question where like the answer is the square root of 2 apples. So like real numbers don't necessarily like count things in the traditional sense, though you may be able to sort of make sense of it. Anyway, so yeah, so that's all I'm going to say about that. Go watch the video. I'm including it in links both places this is uploaded. It's pretty cool stuff. Okay, so the general other thing is if the other fact we need to sort of handle this case in general. So if y equals, let's say, f of t plus I times g of t, is a solution to some homogeneous linear equation, then f of t, oh, and I should say with p of t and g of t, q of t real valued, then f of t and g of t are also solutions to this equation. All right. So let's look at 2 more examples, and then I'll do an exercise, let you guys go. So let's solve, by which we mean find the general solution to y prime plus 5y, y double prime plus 5y equals 0. Okay, so r squared plus 5 equals 0. Let's move it over. R squared equals 5. So negative 5. So r equals plus or minus the square root of 5 times I. So let's think about this then. E to the square root of 5i times t. Well, we can write that as e to the I square root of 5t. And that is cosine square root of 5t plus I times sine square root of 5t. So sort of by this thing up here, cosine of square root of 5t and sine of square root of 5t are a fundamental set of solutions. Our fundamental set of solutions, I mean, you can verify that by calculating this if you want. I believe you should get here just the square root of 5 is the answer, which of course is still non-zero. Okay, so then we have our general solution, y equals c1 cosine square root of 5t plus c2 sine square root of 5t. Let's look at one more example. So solve y double prime minus 6y prime plus 13y equals 0. So r squared minus 6r plus 13 is the characteristic equation. I'll complete the square again, negative 13 over there. If we divide negative 6 by 2, we need to get 3. So we're going to add negative 3 squared to both sides. And we get negative 4 on this side, and r minus 3 squared on this side. So we should get r equals 3 plus or minus 2i. Okay, so this is a little bit different because we have a mixed thing here. It's not purely complex, but we can still figure out what this is going to be. So sort of, naively again, we have 3 plus 2i times t. And let's use the rule here. So we can split that up. First we'll distribute. And then remember, if we're adding in the exponent, we can rewrite that as a multiplication. Use our Euler's formula. And now we'll take the real and complex parts separately. So we'll have our fundamental set of solutions and then our general solution, y equals c1 e to the 3t times cosine of 2t plus c2 e to the 3t sine of 2t. All right, so in summary, so if we consider if the characteristic equation as the first case we dealt with, right, was 2 distinct real roots. Then our fundamental set of solutions is e to the r1t and e to the r2t. In case 2, if we have one repeated root, then our fundamental set of solutions is e to the r1t and t times e to the r1t. And lastly, if we have complex roots, in which case it's always going to be to the form r equals, r plus or minus I, or I'm not going to use r, I'll say alpha plus or minus I times beta, then we can see that our fundamental set of solutions is going to be e to the alpha t times cosine of bt and e to the alpha t times sine of bt. All right, I want to do one more example of this just to, again, sort of emphasize the level of work you're expected to show on exams. So r squared plus 2r plus 10 equals 0. Again, I'll complete the square. R squared plus 2r, negative 10, and then we need to add a 1 to both sides. So we get r plus 1 squared equals negative 9, and r equals negative 1 plus or minus 3i. You don't necessarily have to write out that full thing. We just know it's of this form, so our fundamental set of solutions is e to the negative t times cosine of 3t, and e to the negative t times sine of 3t. And so our general solution is c1 e to the negative t cosine of 3t plus c2 e to the negative t sine of 3t. Don't necessarily have to show this every time. The reason I'm including it is it's about to be something that we're going to need to show, and also just something that's going to be really, really useful for helping organize our work. Basically, when we get to solving non-homogeneous equations, which are equations that look like this but aren't equal to 0. All right, so let's end it on just 3 exercises. So find the general solution to the following 3 problems. So for the first one, let's do y double prime minus 12y prime plus 36y equals 0. For the second one, we'll do y double prime minus 12 plus 35y equals 0. So the only difference between these two problems is that's 36 is a 35. And for the last one, we have y double prime minus 2y prime plus 5y equals 0. All right, so pause here, take a second to work on those. All right, and let's just go over the answer. So I'm just going to indicate what the roots you should have gotten were and the general solution. So you should have gotten here a single root repeated of 6, and that's going to make your general solution c1 e to the 6t plus c2 e to the 6t. I'm sorry, t e to the 6t. For this second one, you should have gotten 2 roots. R is 5 and R is 7. And that's going to make your answer, that's 7. Y equals c1 e to the 5t plus c2 e to the 7t. And lastly, for this one down here, should have gotten complex roots. R is 1 plus or minus 2I. And so then our answer is y equals, another way I can write this, I can pull the e to the t out front. Oh, and I can forget the insides. Okay, 2t plus c2 sine of 2t. All right, so that is the end of that. We will start next class talking about non-homogeneous equations.